Great. So I thought I would use this 15 minutes to talk about 3 characteristics of a modern grid, then talk about how those characteristics might be clashing with current institutional structures, which take a really long time to change also. And I thought I'd add that element into the conversation. Then talk about possible solutions to make that modern grid, those characteristics happen, and then what technology R&D needs might come out of all of that. And maybe you guys know the answers to those R&D questions, and together we can solve this whole thing. And then I guess I wanted to end with just a couple of open questions for further discussion. So just to start with the first element, so many different people think about modernizing the electric grid in different ways. So I'll offer these, and then we can have a further discussion. So the first one is many more modular elements rather than few large ones. So small things that are faster to build, small in a relative sense, not all distributed or something like that, but perhaps smaller than the large baseload units that we may have seen before. They're faster to build and also more continuous in terms of their capacity that they're able to offer either demand-wise or supply-wise. So it's less lumpy. So this clashes with the classic institutional view on reliability, because we've kind of had this system where we have this base load set of resources that we can dispatch to meet this variable demand. And in a world with lots of modular and small pieces, we're going to need to start thinking about reliability in a more statistical way. So there's lots of different elements that need to be co-optimized, and each of these elements can operate within certain parameters that together as a portfolio keep supply and demand in balance. That's quite different from the way that we think about reliability now and how our institutions have been set up to handle reliability. As far as the R&D that would need to go into making all of this work would be to think about actually how do you define those parameters in a way that can interact with the other elements that you're going to have on the supply side and the demand side. And then also the way that we send out financial signals right now, I think in the future could have major consequences if we have a lot more dynamic demand responding to those financial signals. So if we send out a signal at 9 p.m. for everybody to, all of a sudden power gets cheaper and everybody starts charging their electric cars at that very moment, we will end up with a very spiky situation. So thinking about ways to randomize dispatch or randomize the way that financial signals are sent out for different technologies to respond to. So that's one. The second characteristic is a more networked and multi-directional system. So this is thinking about the way that the transmission system now is set up, where there's many different interconnections happening, versus the way that the distribution system is set up, where you hit the substation and then it turns into this radial architecture where we're going in one direction and that's it, unless you're talking about New York City or something like that. So thinking about ways to network the distribution system better into the transmission system, as well as to connect transmission systems on larger scales. And right now, our structures are defined around assets in a lot of cases. So there's planning around, how much nuclear are you going to have, how much wind, how much solar, and not so much around the services that all of those technologies and opportunities are providing. So starting to think about in wholesale markets, in utility planning, how do you start to define these services that we know we're going to need on a longer term basis in an asset neutral way? So start thinking about drawing out what kinds of flexibility we might need, and then allowing many different kinds of technologies to compete to provide that flexibility or whatever grid service we are going to need. So in order to do that, we need more information about the state of different technologies on the grid. So in the demand sector, we need to know kind of what's available as far as demand response. We need to know what the state of charge is for storage at the bulk system level or at the distribution system level. And we also need to know kind of what weather patterns are coming in and making different types of supply available. So that's a lot of data that is going to be needing to be collected and organized. And I think one piece there that people are not necessarily talking about as much is taking advantage of the existing kind of sensors that are out there and taking advantage of the existing communications networks rather than rebuilding, by the utility, their own sort of additional network on top of all of the resources that we already have. So I think also, a big R&D piece around making all of this work with the more networked and multi-directional flow is to begin modeling co-optimization of distribution system assets and transmission assets. And that's a really big piece that I think we have not quite cracked the nut on it yet. But it's going to be one of those I think foundational elements where you start to break down that inherent incentive that utilities and markets have under the current institutional framework to build out additional capital and not sort of co-optimize and take advantage of the latent flexibility and value that's in the existing system. So the third characteristic of a modern grid is to move beyond base load into a more dynamic system. So that's, again, all about co-optimizing supply and demand, and we're looking at a system with a lot more CapEx, and then we build a bunch of stuff and there's low operational costs or low marginal costs. And much of our system today is designed around least cost dispatch, taking into account the marginal cost at a certain time, right? But that whole paradigm is likely to be challenged, especially in a scenario where you have a lot of elements that are on the grid that are available and not available at different times, and you're trying to take advantage of demand side resources. These things don't really, they kind of clash with that least cost, marginal cost dispatch paradigm. Another element to sort of think about clashing into that is the availability of thermal generation. And if we're looking at a system that has less thermal inertia in it, and we're getting our power from different sources that are less thermally dependent, then all of a sudden this unit commitment on a day ahead basis and this hourly what's going to be available becomes a lot less critical. And what's more critical is the longer term timeline of planning what portfolio of resources you're going to have available, getting those resources built, and then being able to dispatch those resources on a near real-time basis with power electronics or with all these sorts of faster reacting elements. So how does that, what do we need to do to realize that characteristic of the electric grid? Definitely new dispatch rules that are not based on marginal costs will need to be explored and figured out in the near term so that we can be there and ready when we have a higher penetration of resources that have low marginal costs. And I don't think there's been a ton of thinking about exactly how you dispatch a system in that world. But ideas could be around maintenance schedules of these technologies once they're built, could be dispatched around carbon content, could be dispatched around other environmental constraints. So those start to become real possibilities as we move into these new electric grids. And then as far as R&D going into this, a lot of the dispatch software is, of course, oriented around what pieces of the grid you have available. So, the characteristics of a nuclear facility, the characteristics of a wind facility. But if we start to think about what kind of flexibility we might need, what other kinds of grid services we might need, and define the dispatch around those grid services, then we end up enabling a lot more technologies to participate in these markets and to cause these changes to happen faster. So I think coming up with a new sort of way of thinking about dispatching is going to be a huge piece of solving this puzzle. So I wanted so again, let me just, the first characteristic is more modular elements rather than large ones. The second characteristic is a more networked, multi-directional flow grid. And the third one is thinking beyond baseload to more of a dynamic system, which co-optimizes across supply and demand. And then I wanted to just throw out there a couple of open questions that I think are worth considering that we haven't talked about yet. One is just about DC versus AC power. And that's a question that, when we were thinking about the last 20% or this 80% sort of timeline becomes really important. I mean, even already today, we only have about 10% of global demand is synchronous motors, and that's kind of the reason why we ended up with this, one of the main reasons we ended up with AC to begin with. And we have a lot more opportunities with power electronics to adjust voltage that we never had when we decided to go down this path of AC power. So this would, of course, be a huge change, but talking about that sort of, low-hanging fruit and moving toward the higher and higher, more expensive, but perhaps transformative technologies, this could be a very important one, seeing as 90% of our demand could be met with DC and done more efficiently that way, so we're not converting back and forth. And then, of course, earlier this morning we did talk a bit about interactions with other systems. That's going to be, I think, a growing concern for the electric grid. How much of the other energy that's currently not electricity will become electricity, and what does that mean for water interactions, and what does that mean for mobility interactions as well. And I think that, especially if you imagine a world where there's a lot more renewables and fewer thermal kind of resources, I think there's a huge amount of opportunity in that to sort of reduce the impact on other environmental systems, water systems, and also to integrate well with vehicles. So that's all good stuff to keep talking about. Thanks.